another interesting interaction parameter which is called scalar coupling. I discussed a lot about scalar coupling and I did mention it is covalent bond mediated interaction. That means one spin will give its polarization or magnetization to another spin for which it is interacting through what is called covalent bond. And there are several features I discussed about the scalar coupling, including the scalar quantity. One spin can exhibit homonuclear coupling, heteronuclear coupling, and one spin can simultaneously experience several couplings of different interaction strengths, and then one spin when it interacts with another spin there is a multiplicity of the transition because of splitting of the energy levels, and as a consequence there will be complex multiplicity patterns. This multiplicity pattern depends upon the number of spin states available for the coupled spin. This is what I explained to you, taking the example of two interacting spins A and X. When A wants to couple with proton X, then it will see X in two possible spin states alpha and beta. Similarly, X will see A in two possible spin states alpha and beta with different energies. As a consequence, I said we are going to get doublet for two of them. Like that we discuss a lot of things and introduce quite a bit about the scalar coupling. I took the example of only two protons and I said maximum of 4 transitions you can get for two coupled spins. And then if what happens if one proton is coupled to many other protons or one proton coupled to several groups of protons, what will happen? How the multiplicity comes? All those things we have to discuss. This understanding of the multiplicity pattern is very important when we analyze the spectrum of proton or any other nuclei where there is a complex multiplicity pattern. Unless you know the pattern, what is the type of splitting pattern we get when one spin is interact with another spin or group of other spins or chemically equivalent or magnetically equivalent spins, how the splitting arises. All those information is needed. We will try to understand this today by taking a lot of examples. Okay, let me continue with this and I will start discussing about the multiplicity pattern of coupled spins. First thing, of course, we discussed this at stretch also. Transition, if you consider in a single isolated spin of nucleus, I took the example of CSCl3 where we have only single proton. I am not worried about interaction with carbon 13 or chlorine. Then we have only two possible energy states, m equal to minus half and m equal to plus half, and the transition between these two are allowed as per the selection rule, which I said changing the magnetic quantum number between any two states should be either plus 1 or minus 1, and between these two states both the transitions alpha to beta, beta to alpha are allowed. So, as a consequence when this transition takes place we are going to get a single peak. This is what we discussed earlier also when we discussed some interaction parameters. So, this is the simple logic. An isolated proton without any coupling to any other spins always gives a singlet because there is no interaction at all. As simple example like CSCl3 or chemical shift, when I was explaining I said reference is TMS. Use TMS. If it does not interact with any of your molecules, all 12 protons of tetramethylsilane are magnetically equivalent. As a consequence it gives a single peak even though there are 12 protons. Like this, when there is a single proton or groups of protons which are chemically or magnetically equivalent, if they do not interact with any other spin, you are going to get a singlet. It is a uncoupled spin. It is called uncoupled spin. Now we will understand how do we get the transition when we have more number of spins. Simple example, after a single spin it should be 2 spins. When we take the example of transition in 2 spins, these 2 spins could be interacting or non-interacting. That means they can be coupled or uncoupled. They are not coupled at all. If they are coupled, that means there is a scalar coupling interaction between them. If there is no coupling, the interaction GAX is 0. However, there are 2 different spins, chemical shifts are entirely different. Delta A and delta X are 2 different protons, 2 different chemical shifts, one for A and one for X. I have assumed a situation JAX equal to 0. That means there is no coupling at all. An hypothetical molecule we will consider here, proton A and proton X, and we assume there is no coupling between them. In such type of molecule there will be cis trans coupling, we will not worry about that. For this special case we assume there is no coupling and JAX is 0. When I look at this spectrum of this, for example, X proton, it gives rise to a single peak. A singlet is detected for X. What about A proton? A also gives rise to a singlet because there is no interaction between A and X, and I take this intensity as 1. There is no splitting. If one proton is there, I told you the intensity corresponds to the proton count. Earlier I said when I was discussing chemical shifts. So, each of them is a single proton, A is single proton, X is single proton, we get only equal intensity peaks, one peak for each of them. If I assume the chemical shifts of X, delta X is very much larger than A, that is the condition we have to consider for AX spin system, we will discuss later. Then if I assume the condition, chemical shift of X is more than that of A, delta X is larger than delta A, then I can simply say this is the spectrum we get for two uncoupled spins, one for X and one for A, two singlets of equal intensity. Now, what will happen? Transition into weakly coupled spins, in which case chemical shifts are different, AX, A and delta X, like in the previous example, they are different. But in this condition, I am assuming JAX is non-zero. That means there exists an interaction between A and X. Further, I have assumed the condition chemical shift difference between A and X spin. If A is here, X is here, I can calculate what is the chemical shift of A and chemical shift of X and take the difference between these two. I call it as delta chemical shift difference between A and X spins, and I assume this to be very much larger than coupling constant. This is the assumption. Now, let us see what happens to this type of interaction when for two spins which are weakly coupled. But remember one thing I want to tell you, interactions in NMR are always mutual. That means if A spin is interacting with the X spin in a molecule, X is also interacting with A. The interactions are always mutual. Now, if proton A is coupled to X, proton X is also coupled to A. It is a mutual interaction. If peak of proton A is split into a doublet because of X, then obviously the peak of proton X is also split into a doublet because of A. Proton A will see X in two spin states, similarly proton X will see A in two spin states, each of them will be a doublet. So, interaction is always mutual, that you must remember. Now, when there is a coupling pattern, what is the type of coupling pattern we are going to see between two non-equivalent spins? They have to be non-equivalent. As I said, if they are equivalent, there won't be any coupling. When the chemical shifts are overlapping, exactly equal, of course, there could be coupling, but we are assuming that they are non-equivalent now. This is a hypothetical molecule again, A and X, assuming there is no other protons, only two protons in this molecule. Consider proton A. It has two spin states alpha and beta. Proton X also has two spin states alpha and beta. Since JAX is non-zero, there is an interaction between them. Proton X sees proton A in these two orientations alpha and beta, and then it splits into a doublet like this. Exactly from the center, look at it, exactly from its center of position of chemical shift, it starts splitting into two lines exactly from the center, two peaks and move on either side. Fine, that is a doublet. What happens to proton A? Proton A now sees proton X again in two peripheral orientations for X, that is alpha and beta. Exactly identical phenomenon. What will happen? X will also move into a doublet. Two peaks it gives exactly from the center. One peak moves at equidistance to the right, other peak moves at equidistance to the left. And if you measure this separation, that is called JAX, coupling constant between A and X spins. Since the mutual interaction is mutual, as I said, if this is JAX, this also has to be AX. There is no difference because interaction strength should be same because they are interacting equally. Both A interaction with X interaction with A are identical strengths. So, this is how when we have two protons, if there is a non-zero J coupling, each of them will give a doublet. Please remember, center of this doublet correspond to respective chemical shift. If this correspond to X, the center of this correspond to chemical shift of X. If this doublet corresponds to A, center of this doublet corresponds to chemical shift of A. Okay, that is how it is. Interestingly, you have to see one peak split into two with equal intensity 50-50. This is the equal intensity peak. So, total intensity should remain same, that is what I said. So, one peak split into two, now intensity has come down by half for both of them. This is the pictorially you can understand this. The proton A and proton X both are there. So, when proton X and if you consider proton A, this is because of X has two lines, one goes to the right, other goes to the left, equidistant, this is called J by 2, this is called J by 2, where J is the interaction strength between A and X and exactly center is the chemical shift of A. Same way, if I look for the X, X will see A in two states. So, again it will have two peaks, one move to the left, one move to the right with identical strength. This is how in reality I am showing for individual protons, but in reality both will be simultaneously present. As a consequence, you are going to get two doublets. When two protons are coupled to each other, you are going to get two doublets. Okay? Two non-equivalent spins, when they each proton will split into a doublet with identical separation, and intensity is equally divided into two peaks, 50-50% will be intensity, and the separation of this doublet is the measure of your coupling strength JAX. That is the thing which you should remember. Okay. As I already said, center of this doublet gives corresponding chemical shifts. How the spectrum of two coupled spins is seen in a real spectrum. In reality, consider a molecule like this. A real molecule, there are only two protons. Of course, OMe is there, methoxy groups. We will not look at that spectrum. Only spectrum corresponding to two protons of the phenyl ring. If you consider, you get two peaks, one here, which look each one for A proton, one for X proton. If the coupling was not there, each would have been stringlet at the center, but now because of the coupling, it is becoming a doublet. Okay. A will see X into two spin states, X will see into two spin state, and this separation measures gives you JX. It is a real spectrum, reality, not a hypothetical spectrum of the stick plot which I did earlier. This is a real spectrum of a molecule. Now, there will be more complex multiplicity pattern. In reality, you are not going to see only this type of simple doublets. Very complex multiplicity pattern will come. We will see what are the more complex multiplicity pattern, how do we see that. Before that, I want to tell you what is the splitting pattern we get by using what is called a family tree approach. When one proton is coupled to n other protons and each of them should be chemically non-equivalent. One proton, let us say proton 1 is there, it is coupled to other proton 2, 3 and 4 etc. Then what will happen is each is split into the because of its coupling with the other one with the different strengths, and you can generate this multiplicity pattern by using what is called a family tree approach. That is what I will show you now. Let us say one proton is coupled to two protons. I consider this is the proton A, M and X. Let us look at the proton X, which is highlighted here, the colored one. This is the singlet. Assuming there is no coupling between A and M, it has to be a singlet with intensity what? 100%, or take it 1, intensity is 1. This X can couple with A, 3 bond coupling is there, cis coupling, and because A can have two possible orientations individually, then X will split into doublets. Now, what is the intensity of the doublet? This total intensity has been divided into 2. So, it will become half 0.5, 0.5, and the separation is coupling between A and X. What is happening to the third proton M? It is not sitting idle, that can also couple with X. Okay. Now bring the coupling of X with M. M has again two possible orientations, alpha and beta. What will happen now? This each of these doublet lines split further into two lines. 1 became 2, now 2 became 4. What will happen to the intensity now? Again it has to get distributed. So now the intensity become this separation, of course, is coupling between M and X, this is coupling between A and X, and this separation between M and X. Again intensity now is 0.25, 0.25 and 0.25, 0.25. But as I told you, the total intensity should always match with the uncoupled proton. This is how you can generate the multiplicity pattern using the family tree approach. You may ask me a question, I saw only proton X here. What happened if I look at the signal for proton A and proton M? It is also possible, right? And when I see proton A, it will couple to X and it will couple to M. When I see proton M, it will couple to A and it will couple to X. So identically what is happening is similar pattern is going to be observed at the chemical shifts of protons A and M. Now at the chemical shift of proton X, we saw 4 lines because of its coupling with A and M. But now if I go to the chemical shift of A, at the chemical shift of A, we have again 4 lines because of A coupling with M and X. At the chemical shift of M, again you get 4 lines because of M coupling with A and X, and this is the similar pattern you are going to get. Okay, that is how when 3 protons are coupled to each other, each proton will give 4 lines. So 3 protons together will give rise to 12 lines, 12 peaks you are going to get. What happens if I extend this molecule? Let us say we have 3 protons, 1, 2 and 3. Now I have added one more P, AMX was there, I added P. How does the spectrum come now? Extend the logic same way. X will couple to A, becomes doublet. It will couple to M, become doublet of doublet. This separation is JAMX, this is JAX. Coupled to P, each will be further split into half. Then this becomes JPX. This is the intensity 1, become 0.5, 0.5, 0.25, 0.25 here. Here half of that 0.125, 8 lengths. So 8 into 0.125, again we will get same intensity. This is the pattern you get when one proton is coupled to 3 other protons which are non-equivalent chemically. So 8 lines you get. What happens if I look for the, this is for the proton X. What happens if I look for the proton A, M and P? Extend the logic. Identically at the chemical shift of A will couple to M, P and X. At the chemical shift of M will couple to A, P and X, and P will couple to A, M and X. So at the respective chemical shifts you are going to get 8 lines each. So when totally one spin is coupled to 3 other spins, you get 8 peaks for each of them. There are 4 such protons, totally you are going to get 32 peaks. That is the type of pattern you are going to get. Now let us see the multiplicity when n non-equivalent protons are coupled. This is the summary. One proton coupled to another single proton gives doublet of equal intensity. When one proton is coupled to 2 different protons, we get 4 lines of equal intensity. When it is coupled to 3 protons of different chemical shifts, different chemically inequivalent protons, you get 8 lines of equal intensity. So simply you can generate a formula. One will, it is 2 to the power of 1, this is 2 to the power of 2, this is 2 to the power of 3. 2 to the power of 1 is 2 lines, this is 4 lines, this is 8 lines. So the number of peaks which you are going to get when one proton is coupled to n other protons is given by 2 to the power of n. The splitting generates 2 to the power of n lines. So if n is 4, 2 to the power of 4 is 16. If n is 3, you will get 8 lines like this. That is how when one proton is coupled to n chemically non-equivalent protons, the total number of lines at the site of each individual proton is 2 to the power of n. Remember that. So this is what I said for the example of A, M and X. A gives 4 peaks due to A, M and AX, M gives 4 peaks due to A, M and MX, and X gives 4 peaks due to AX and MX. Okay. This is for n chemically inequivalent coupled protons. General, you write down the formula. The number of lines at the site of one of the observed protons is given by 2 to the power of n minus 1 total. And if there are n peaks, number of protons are n, then the total number of peaks is given by this equation, sigma summation of total number of protons n into 2 to the power of n minus 1. Simple logic. If I have 4 protons, each proton will have 2 to the power of 4 minus 1, 2 cube, 8 peaks. 8 into 4, 32 peaks, n is 4. So, totally you can using this formula, you can find out how many peaks you are going to see at the chemical set of individual protons and how many peaks totally you get in the entire spectrum. That can be understood by this equation. And this is a simple pattern. It is a realistic spectrum, it is not a stick plot. For example, here one proton is coupled to 3 other protons. How many peaks we should expect? I told you one proton is coupled to 3 other proton, 2 cube, 8 lines. You see, you can count here, there are 8 lines, here 2 are overlapped, so it will be 8 lines. When one is coupled to 4 protons, it should be 16 peaks. See, some are overlapped, we have written the intensity here 1, 2, 1, 1, etc. Add up all the intensity, you can see a number of peaks, you can count number of peaks. Each peak is one intensity. So, if there are 3 peaks here, 3 here, 2, 2 here, if you add up everything, you are going to see 16 peaks here. If one is coupled to 5 protons, you are going to get 32 peaks here. That is a reality. Okay, this is a real spectrum. How you get this is at the site of one proton. Then the entire spectrum, for example, 32, there are 5 protons. If one is coupled to 5, there are 6 protons, then 32 into 6 is the total number of peaks you get in the entire spectrum. This is the simple formula we should understand. You understood now the simple multiplicity pattern, how we generate using the family tree approach, and the formula we obtained about getting the number of peaks at each chemical site of proton and total lines in the spectrum. Here now I am going to introduce another term called active and passive couplings. What is an active coupling and what is a passive coupling? Look at the number of protons I have written here. There are 5 different protons, all are chemically inequivalent. I have numbered it 1, 2, 3, 4 and 5. Proton I am going to see, and I am sitting at the chemical shift of proton 1. The chemical shift of the particular proton which I am seeing is called an active spin. Remember, this proton which I am observing is an active spin. Then the remaining are passive spins. If I go to the chemical shift of the proton 2, then that is active spin, the remaining are passive spins. Now let us see, I go back to this, I look at the proton 1, that is an active spin. To me, all the remaining 4 are passive spins. Now what will happen? 1 can couple to 2, 1 can couple to 3, 4 and they are called active coupling. For the active site at the proton 1 which we are detecting, for the active spins, for the active spin all the remaining passive spins are coupled, that is called active coupling. Remember the statement, coupling of active spin with all the passive spins are called active couplings, which you are going to see at the proton site, at the site of this proton 1. And for that matter, the one coupling may be 0, it may not exist, does not matter. But these type of interactions, coupling of 1, 2, 1, 3, 1, 4 gives multiplicity at the site of proton 1. How many multiplicity you get now? Because it is coupled to this, become doublet, doublet of doublet and doublet of doublet of doublet, 8 lines you get. Because one coupling is absent, at the proton chemical shifts you get 3 couplings, they are called active couplings. Now what will happen to the other things? Other coupling is there, 2, 5 is coupling, there is a coupling between 2 and 5, 3 and 5, 2, 3, all other couplings are there, many other couplings are there. They are called passive couplings. Please remember, they are called passive couplings. These passive couplings are not shown at the chemical suite of proton 1. At the chemical state of proton 1, these passive couplings are not seen. You understood? Active coupling is the one where at a particular site of the proton you go, that is active proton, with respect to that, all other couplings of the passive spin is seen, that is called active coupling. Whereas all other couplings apart from this proton, remaining other passive couplings among the passive protons are not seen at the chemical sheet of proton 1. This is a simple logic you should understand. You may extend this logic. What happens instead of proton 1 I detect proton 3. Now what is my active spin? My active spin is proton 3 and 3 can couple to 2, 1, 5 and 4. So there are 4 active spins of coupling strengths different. These are all called active spins, and these couplings will be seen at the chemical sheet of proton 3. So proton 3, when you analyze that spectrum multiplicity, you get 2 3 coupling, 1 3 coupling, 5 3 coupling and 4 3 coupling. What about the other things like this 2 5, all other remaining proton couplings, they are called passive couplings, and these passive couplings are not seen at the chemical site of proton 3. Now you understood what is the difference between active spin and passive spin. Active spin is the one which is detected or at the chemical sheet of the particular proton, and that proton when it is coupled to remaining protons which are called passive protons, that coupling is seen at that particular chemical shift, whereas coupling among the remaining spins are not seen there. So for that you have to go to particular chemical sheet of other passive spin. That is the important concept. This is the concept. This concept has to be very clear for you if you have to analyze a proton NMR spectrum or any NMR spectrum. Active and passive coupling is important. So if I look at the proton 1 and if I want to see the coupling 3 4, you will not see that. You cannot get it because there is a passive coupling. So you should know the difference between active coupling and the passive coupling. Okay. Active and passive coupling is a homonuclear coupled spins. I will show you. For example, this is a molecule A, M and X. Realistic spectrum we will take. I will give you an example now what is happening for active coupling and passive coupling. I am looking at proton A. This is chemical sheet of proton A. That is an active spin. So what are the couplings you get here? You get the coupling between A, proton A with M and X. So you get coupling AM and AX, they are active couplings. What is the coupling between M and X? See, we are detecting a coupling between these M and X, they are passive coupling. That passive coupling you will not see at the chemical sheet of the proton A, which is active spin. Passive coupling MX is not seen, other two couplings are seen, they are active couplings. Okay. This is how we can measure. Now let us go to the M. Now this is the chemical sheet of M. What are we seeing here? At the chemical sheet of M, we are going to see active couplings AM and MX. They are the active couplings. What about the coupling between A and X? They are passive spins. That passive coupling is not seen at all. Okay. Go to the next one, proton X now. This is the chemical sheet of proton X. That means that is the active spin. At the active spin proton we get AX coupling and MS coupling, but the AM coupling passive is not seen. That is how we can start analyzing, and we know what is the active spin, what is the passive spin and what are active coupling and what are passive couplings. This information is essential. You should understand this, only then you can interpret the spectrum, analyze and extract the coupling. You cannot look at this one at proton A and start looking for the MS coupling, you will not see. This is a very important concept, you must remember. Okay. Let us see active and passive couplings in a heteronuclear coupled spins. I will show you an example. Let us take the example of 13C labeled dibromofluoromethane. This is a molecule. Okay. Now with the weakly coupled spin system we have A, M and X, 3 protons are there, 3 different heteronuclei is there, and this is a proton spectrum, this is a 19F spectrum and this is a carbon 13 spectrum. And if proton is an active spin, if this is in the proton spectrum, that is the active spin, fluorine and carbon are passive spins. So at the proton spectrum when you analyze, you will get JCH and JFH, but what you are not going to see, JFC you will not see, that is not possible, you will not see. Similarly go to now fluorine NMR. Fluorine is an active spin, proton and carbon are passive spins. So, at the when you analyze the fluorine NMR, you get JFH and JFC, but you do not get JCH, you will not get. Similarly, now go to the last one, carbon 13 is an active spin, this is carbon 13 NMR, what do you get now? JHC and JFC you are going to get. What you do not get? JHF you do not get, that is a passive spin. This is how you can understand when you analyze the spectrum, but that is homonuclear, heteronuclear, what is active coupling and passive coupling. So, since the time is getting up, I am going to stop here. So, today what we discussed in this class, I started introducing to you about the multiplicity pattern that we are going to see when one proton is coupled to several other chemically inequivalent protons. When one is coupled to other proton, I said each will be a doublet if I look at both of them. If one is coupled to 2, each it will be each of them is going to be 4 lines because 3 coupled spins are there. If I have 4 coupled spins, each spin will couple to remaining 3 other spins will give 8 lines each. The total number of lines in the spectrum is given by n into 2 to the power of n minus 1 is the total number of lines in the entire spectrum. At the chemical structure of each of them, you are going to get 2 to the power of n minus 1 transitions. That is what we understood, how the multiplicity is going to be obtained. And I said one line is split into 2, 2 into 4, in intensity keeps drastically coming down in the same ratio, each of them will be divided by 2. But the total intensity of the multiplicity remains same as the uncoupled proton, it does not change. Total multiplicity, integral area of the multiplicity and the uncoupled proton should remain same. This is what we understood, and you also understood about active spins and passive spins. What is an active spin and what is a passive spin? Active spin is the one where you are going to detect the particular spin, for example particular proton chemical shift. There are other protons in the molecule, they come at different chemical shifts, then they are passive, that you can't consider them as active. So, at the site of the active spin you get coupling between this proton and the remaining protons, and the proton coupling between the remaining protons or passive coupling is not reflected at the active site. And this is how we know if I analyze a particular group of multiplicity pattern, what are the couplings we can extract, what we can get, we can interpret and analyze and interpret the spectrum. So, this is what I summarized today. We will stop here and we will come back and continue with this in the next class. Thank you.